All right, everybody. It's time for us to head for home in this unit. It's week 3 of Unit 5. Unit 5 deals with differential equations and mathematical modeling in general. On today's show, the big topic of partial fraction decomposition. In this lesson, we use some pre-calculus mathematics to bail out our calculus mathematics by breaking up fractions that seem to be hard into fractions that aren't hard. Let's pretend that I wanted to find this integral. This integral, let's see, every trick we know. Why is it not good for this? Gosh, it's not a u sub, because the derivative of that is 2x, and we don't have an x anywhere in the problem. So it's not going to be a u sub. It doesn't look like integration by parts. It doesn't look like anything I know how to do, but I do know that 25 over x squared minus 25 has a factorable denominator. And the curious thing from pre-calculus mathematics is that when we have a factorable denominator and our fraction is proper, by proper we mean that the denominator has a larger power than the numerator. When we have a proper fraction with a factorable denominator, that can be broken up into two fractions, proper fractions, whose denominators are the factors. If I add two proper fractions, I'm going to get a proper fraction. There's some good pre-calculus mathematics that goes into that. And so we can reverse the process and say if I have a proper fraction whose denominator is factorable, I get two proper fractions that add up to it. Now here's the glory in that. Since the denominator here has a power of 1 on the x, the numerators, in order to be proper, cannot have a power of x at all. They can't have a power of x bigger than 0. So the fraction on the left has to be some number over x minus 5, and the fraction on the right has to be some other number over x plus 5. And then pre-calculus kicks in. How would we combine these two fractions? We would multiply everybody by the other's denominator. We would multiply everybody by the other's denominator. We would put that over x minus 5x plus 5, and we would set it equal to 25 over x minus 5x plus 5. So all I have to do is figure out the values of a and b that make this true. And that is easy peasy. We're going to let x equal 5. And by letting x equal 5, we are going to drop that term right out of there. So if x is 5, then let's see, 5 plus 5 is 10, that's 10a. 5 minus 5 is 0, that term drops out. And so a is the fraction 5/2. Similarly, we're going to let x equal negative 5. And by letting x equal negative 5, we're going to drop that term right out. Negative 5 plus 5 is 0. That's going to drop right out. Negative 5 minus 5 is negative 10. And so b is the fraction negative 5/2. How does that help us out with an integration? Well, all that stuff in red means that the black fraction is the same thing as 5/2 over x minus 5 minus 5/2 over x plus 5. And those are two integrals I know how to take. The fraction on the left integrates to 5/2. natural log of x minus 5. The fraction on the right is also a natural log plus a constant. And we know from our work with natural logs that when you subtract natural logs, what you're really doing is dividing their arguments. There's those laws of logarithms come to play. And we use pre-calculus mathematics to bail out our calculus. Don't believe me? I'll do it again. Integral of 2x plus 16 over x squared plus x minus 6 dx. This thing is a proper fraction. Since it's a proper fraction with a factorable denominator, and that denominator does in fact factor, that proper fraction is the sum of two proper fractions whose denominators are the factors. Since the smaller fractions are proper and the denominators are linear, the numerators cannot be linear. They cannot be any bigger than constant terms. Cannot be. And so what happens now? How would we combine two fractions with different denominators? We would multiply everybody by the other guy's denominator. We would put that over x plus 3 times x minus 2, and we would set that equal to 2x plus 16 over x plus 3x minus 2. The denominators are irrelevant. We equate the numerators. Now we need strategic substitutions. If we let x be negative 3, then this term drops right out, and we get 2 times negative 3 plus 16, that's 10. Negative 3 minus 2 is negative 5a. A is negative 2. If we let x equal 2, then this term will drop right out. And so we get 2 times 2 plus 16. The 2 minus 2 drops right out. 2 plus 3 is 5b. And so b is 4. How does that help us? It means that that black fraction at the top is the same as negative 2 over x plus 3 plus 4 over x minus 2 dx. And so we can take those one term at a time. This is negative 2 natural log of x plus 3 plus 4 natural log absolute value x minus 2 plus a constant. Now that's not the way you're going to see it in the back of the book. You're going to see it in the back of the book as the natural log of x minus 2 to the 4th power over x plus 3 squared, and I don't need absolute value brackets anymore because anything raised to the 4th power divided by anything raised to the 2nd power must be non-negative. That's the way it's going to appear in the back of the book because it takes up the least space. And so that's probably the way it's going to pop up as an answer choice. Okay. Okay, I'll go one more just for practice's sake, and then I'll show you where it gets nasty. See if you can follow what I'm doing on this go-around. See if you can understand at every step why I'm doing what I'm doing. I've got a proper fraction with a factorable denominator. So, how does this get set up? The denominators there are linear. Okay. Okay. I mean, if one of those denominators were a non-factorable quadratic, we'd have to have linear terms up top. Something like bx plus c up top. So, okay. What's going on here? Okay. Do you see what your two strategic substitutions are? What are your two strategic substitutions? Okay. Uh-huh. So let's make those substitutions. Okay. I know what A is. Uh-huh. Okay. I know what B is. How does that help me? What's going to go in those big parentheses there? Okay. Okay. And why is that helpful? Because I can do those integrals one at a time. You get a lot of natural logs with partial fraction decomp. And that's not the way it's going to appear in the back of the book. It's going to appear in the back of the book in as condensed a form as possible. And so all your laws of logarithms come back to haunt you. Okay. Okay. Well, one more. What happens if your fraction is not proper? What happens if your fraction is top-heavy? We used to call those Dolly Parton fractions. I don't know what the equivalent is nowadays. I'm old. Speaking of old, this is a good long division problem. How do you do a long division? The same way you did in 3rd grade. There are placeholder zeros in the x place and the constant place, and we ask ourselves, how many times does x go into x squared? Don't say once. X goes into x squared x times. How do we know? Because x times x is x squared. So then what did you do in 3rd grade? You multiplied this by that and wrote the answer here. That's what we're going to do again. We're going to multiply. And then what did you do? You always subtracted. The x squareds go away. You've got an x right there. Then what did you do in 3rd grade? You dropped this thing down and tried again. How many times does x go into x? Now say once. And so we multiply and subtract. 0 minus a -1 is 1. How do we write the remainder? We write the remainder as a mixed number. Remainder over divisor. Just like you did in 3rd grade. Which, of course, you remember like it was yesterday. Like it were yesterday? Like it were yesterday. How does that help us? That means that the black fraction is the same thing as x plus 1 plus 1 over x minus 1. And I can do each of those integrals one term at a time. Easy peasy, done. And that's the kind of thing I expect us to be able to do. I expect us to be able to break up fractions and deal with improper fractions. Okay, tomorrow we'll talk this through, and then there's a full practice day to get us really, really good at this. And I hope you enjoyed it. We'll see you tomorrow.